We are live. What's up, guys? This is Dem Keys, and today we are going to continue learning how to save PyTorch models. Sorry, I had to think about that for a second. Um, but the good news is, well, I mean, I'm saying but the good news as if the fact that we are about to learn how to save PyTorch models is a bad thing. The but was not necessary there, but anyways, so we're going to be learning how to we're going to be continuing where we left off yesterday with learning how to save PyTorch models. Why was I saying but? There was something I was going to add after the but. I can't remember what it was. Well, okay, anyways, so after yesterday, oh yeah, I was about to say that the good thing, the good news, which again, why I don't know, it kind of seems like I'm comparing it to yesterday, or yesterday being bad. Yesterday was great. Cutane, hello, welcome to the stream. How's it going? We are doing another study stream, and I was just about to say that it's great that we are doing two talking streams. Or well, we have done talking streams 2 days in a row. Yeah, that's what I was trying to say. That's great. That's amazing. Once we have learned how to save, I mean, okay, we learned how to save models yesterday, and I'm gonna kind of practice more of that today. But I also want to explore the Torch Dynamo and Onyx side of things. So we're going to be reading up on exporting to Onyx using Torch Dynamo. Give me a give me a second. Yeah. Okay. So that's the plan for today. Um, we're gonna continue learning how to save PyTorch models. Yesterday, I was after yesterday's stream, I continued doing a bit of research on other stuff, not necessarily on the Onyx stuff. Uh, I did I did try to research the difference between Torch Script and Torch Dynamo, because so far what I understood in terms of exporting to Onyx, these are two separate backends that you could use for exporting, and each one has its own way of doing things. With Torch Script, you would need to convert your model to Torch Script, and then Torch Script itself gives you an option to export to Onyx. And then you have Torch Dynamo, where you just convert your model directly. There is something that happens in between, but at least from what I've understood, you don't have to do like an explicit conversion in between. Whatever conversion has to be done, whatever extra steps have to be taken, they're taken by themselves. And there was also this thing mentioned about control flow, as in if your model has control flow related operations, those things have to be handled explicitly in Torch script, but in Torch Dynamo, they get handled automatically for you. And just like that, like there's a couple of other how do I say this? Couple of other details, a couple of other intricacies that you need to take into account when you're choosing between Torch Dynamo and Torch Script. But based on the research that I've done so far, it kind of seems like I should give more of my time to Torch Dynamo right now. And in the future, if there is a need for Torch Script, then I'll look into it. Otherwise, I'm just going to stick with Torch Dynamo for now, because it's not like I can't learn both of them. I can learn I can learn one of them now, and then later on the other thing can be learned if the need arises. It's not like I'm stuck with just one. It's just that I kind of want to choose one. I don't want to spend time learning both of them just at the off chance that there ends up having to be a lot more to explore. Because if there's a lot more to explore, then That's obviously going to take more time as well, right? So I need to kind of use my time wisely, which is why I don't want to spend time learning both of them if I can just learn one of them and make do for now. Another thing that I want to look into is, okay, so I was led to Torch Dynamo when I was trying to learn how to export a PyTorch model to Onyx, to the Onyx format. But from what I've understood, apparently you can use Torch Dynamo to export the model to other formats as well. And I kind of want to explore that as well because I've only looked at it from the Onyx point of view, but I want to see what else is possible in terms of exporting models. And for that, I have opened up these two pages. This one we were already looking at it yesterday, and we're gonna, you know, continue reading this. And then there was actually, okay, hold on. I just remembered there was one more page that I had opened up yesterday, which I did not continue reading. I think it was this one, wasn't it? It was one where we did it redirect by itself. Yeah, this was the one. Is this the one where they load the convolutional neural network? Give me a second. Let me just run through this real quick. I don't think this is the one. Where did I see that? Give me a second. Let me just uh where was it? Cuz I just remembered that in yesterday's stream towards the end, I was looking into um I was looking into saving something, and as an example, it loaded, was it here? Oh, it was here. Okay. It was here. This was where we loaded that convolutional neural network, and then um okay, all right, cool. Oh, another thing I want to look into once I've learned how to save and load models and how to export to the Onyx format. Oh, one more thing, dude. Like I need to. So I'm learning how to export the model to the Onyx format, but if PyTorch happens to have an Onyx runtime, I would also like to load exported Onyx models into PyTorch and try to run the same model and see how that whole system works. Like, how do you go about setting something like that up? I should write this stuff down. Well, I don't think I need to write it down because like in the moment, like when I'm practicing the stuff, then I'm gonna get the idea by myself. Uh, I don't think I need to write it down. Okay, so yesterday we were here. And I remember being a little confused about this part where, so, okay, in this case, there was a difference between loading the model and loading the model's state dictionary. Because, at least from what I understood, the model's state dictionary contains all of the weights and biases. Um, uh, how do I phrase this? It contains all of the weights and biases with respect to the structure of the network, right? But it doesn't contain the structure of the network itself, if that makes sense. And this was claiming, or at least I assumed what this was saying, was that if you use torch.save and instead of passing in the state dictionary, you directly pass in the model, it saves the structure as well. And I was like, okay, that's cool. But then down here, it mentioned something. It mentioned this approach uses Python pickle module when serializing the model. Thus, it relies on the actual class definition to be available when loading the model. So that means that it doesn't. It does. We are not saving the structure of the model here. And if we are not saving the structure of the model, then what's the point? Like, what's the point of use? What are we trying to do exactly when we use this method? Oh, you know what? I think I could ask this question to, I want to say llama, but now I'm just going to say we'll ask this question to perplexity. We're going to use sonar. No, you know what? We can use DeepSeek. Give me a second. I haven't opened up Perplexity Labs here. What was it? Labs.perplexity.ai. I love that they've just provided this thing. Like they're just hosting the models here, and you're free to come and use it. Morty VGC, hello, hello, welcome to the stream. How's it going? We are currently doing a study stream. We are learning how to save and load PyTorch models, and we're also going to be learning how to export to the Onyx format. Give me a second. I'm just opening up DeepSeek here, and okay, now we can ask the question. Pretty good. What about you? I'm okay. I'm okay. I'm happy to be able to stream. Just at the moment, that's all I can say. But I'm okay. I'm I'm happy about the progress that I'm making. What was I what was I gonna ask? Yes. Okay. So I was gonna I was gonna ask DeepSeek. Shit. What was I gonna? Oh yeah. Okay. So I'm learning how to save PyTorch models using torch.save. From what I understand, if we pass in model.stateDict to the save method, it passes the weights, spelled that wrong, weights, the weights and biases. I spelled that wrong as well. Give me, give me a second. There you go. It passes the weights and biases of the model, but not the structure of the model itself. So we would still need to define a class containing the model structure in order to use the weights. I've also discovered that we can pass in just the model itself and not the model's state dict, but that doesn't but that apparently doesn't store the structure of the network. What I'm wondering is if passing the model in alone doesn't store the structure, then what's the point of it? So, okay, if it's not clear what my question here is, while the model is doing its thing, my question here is that, okay, if we pass in the state dictionary, the state dictionary the state dictionary contains the weights and biases, right? It doesn't contain the model structure itself, the structure of the network. So you would still need to define a class that contains the structure. But then we have this section down here, which apparently does, okay, let's read this again in case I missed something. Okay, so when loading model weights, we need to instantiate the model class first, because the class defines the structure of a network. We might want to save the structure of this class together with the model, in which case we can pass model and not model state dictionary. Okay, we can then load the model as demonstrated below. As described in so-and-so section, saving the state dictionary is considered the best practice. However, below we use weights only equals false because this involves loading the model, which is a legacy use case for torch.save. So then it's this thing that's confusing me. This note that's been given here, this approach uses Python pickle module when serializing the model. Thus, it relies on the actual class definition to be available when loading the model. So if the class definition has to be available anyways, then what is the point of saving the model in this way? Or here, in this way? What is the point of saving the model in this way if it's not saving the structure anyways? What are you learning it for? AI, other stuff, or just curiosity? Um, Well, you can say curiosity and AI because I'm learning deep learning. I'm interested in learning how to build these models, and um, I've also been learning data science. And at some point, I kind of want to bridge both data science and deep learning. But yeah, in general, I'm learning both data science and deep learning, and this is one of the things that comes along with that. Currently, we are learning about, so far, I've only learned about feed forward neural networks, or I've only looked into the practical side of feed forward neural networks. I'm yet to go into convolutional neural networks and recurrent neural networks, and at some point, I also want to go into the transformer architecture, but that's for later. For now, I kind of want to wrap my head around the basics of PyTorch, so like building the model, training the model, and well, now saving and exporting the model. So let's see what the answer is here. Okay. Okay, so I'm trying to figure out how saving PyTorch models works. The user mentioned that when you save the model's state dictionary, you get the weights and biases, but not the model structure. This makes sense because the state dictionary is just the parameters. Okay, so to reload it, you need to have the model class defined again. But then they also said that you can save the entire model, not just the state dictionary. Wait, but if that doesn't save the structure either, what's the use of saving the whole model? Maybe there's a misunderstanding here. Let me think. When you save model.stateDictionary, you need the model's architecture to load it back. But if you save the entire model, does that include the structure? I thought that may what? I thought that might be the case, but the user is saying that passing the model itself doesn't store the structure. That doesn't sound right. Maybe the confusion is about how Python objects are serialized. Wait, PyTorch's torch.save uses pickle to serialize the model. So when you save the entire model, it's pickling the model object, but for that to work, the class definition must be available when you reload it. So if you have a custom model class, as long as it's in scope when you load, you can load the entire model. But if you don't have the class definition, like if you save it and then try to load it in a different environment where the class isn't defined, then you'll get errors. So saving the model does save the structure, but it's dependent on the class being available, whereas the state dictionary is just a dictionary of tensors, which is more portable but requires you to rebuild the model structure manually. But the user is saying that passing the model in alone doesn't store the structure. Maybe they tried to save the model in one script, then load it in another without having the model class imported. And that's why it didn't work. So perhaps the answer is that saving the model does save the structure, but it's tightly coupled with the code. So the advantage of saving the entire model is convenience. You don't have to reinitialize the model and load the state dictionary separately. But the downside is that the model class isn't available when loading. What? But the downside is that if the model class isn't available when loading, it fails. Whereas using state dictionary, it's more flexible because you can rebuild the model structure in any way as long as the layers match. So the point of saving the entire model is that it includes the structure as long as the class is available when loading. See, this is what I'm not understanding. The structure is in the class. The structure is defined in the class. So if you have the class defined, you have the structure, right? If saving the model by itself is not saving the structure, and we anyways need the class to be present, we anyways need a class definition to be present, what exactly is being saved? Like, how is it saving the structure? What structure is it saving? Yeah, I'm not understanding it too. Yeah, I'm kind of confused about this. Like, I'm pretty sure there's something I'm missing here, something that I haven't understood because this was my understanding, right? Hold on. Okay, let's do it practically here. You know what? Let's do it practically and see. Um, give me a second. Let me start this thing. Okay, while that's starting, we can open up a new notebook. We can open up a new cell here. Uh, and let's define a new network. So let's say my what is it? Um, what was it? FCNN? Yeah, FCNN. Give me a second. Yeah, my FCNN01, and this has to inherit from nn.module, and then in here we need, I think we needed an init method. I think so. I don't remember. Hold on. I think I'm gonna. Oh wait, we need a self thing here as well. There was also I think we had to call this. Hold on, dude. I'm not able to remember some of the boilerplate code. There was uh there was an init method that we had to call within one of the inherited things. Oh, it's super dot init. Okay. All right. Okay, so super dot init. What does the init thing have to look like? Oh, that still requires the underscore. Okay. Right. So here, um, what do we call it? We'll just call it, I don't know, linear stack equals nn dot sequential, and then in here we can do linear, I don't know, 2, 4, and then relu, and then let's say that. Okay. All right, so this is our very simple network. And then we can define a forward method which takes in x. You know what? Okay, yeah, we can also add in a flatten thing as well. So nn.flatten, and then I'm trying to make this as close to, the one of the boilerplate things as possible. So Just give me a second. What is it supposed to be? I think self dot. Oh yeah, self. I think self is necessary here as well, right? Though we are not calling self explicitly, but self is necessary. And then we can call self dot flatten and then self dot linear stack. Okay, all right. So x equals self dot flatten x, and then return self dot linear stack x. Okay, that should be it, right? If everything is fine here, then we can move on to the next thing. And here we can say model O1 equals my fcnn O1. And here I don't think we need to call forward explicitly. I think we just call the model itself, and then we get. Okay, I forgot what the shape is supposed to be. Okay, let's say tensor, and in the tensor, I think this should work. I always have this confusion. Like, okay, let's try passing the thing in and see if it works. Let's say RO1, and then we can print out RO1. It has no attribute flatten. Should it be this? I think that might be it. And now we have the issue of the size. Not the size, the shape of the tensor. So let's try something here and see if it works. Okay, cool. So this is our model, okay? We don't need any of this. Now we just need to save this model. So if we try to print out the model, then this is our model. We have a flatten function, and then we have our linear stack, which has one linear layer, and then a relu function, and then another linear layer. So if I, how do I, how do I set this up? Because we need to, yeah, no, how do I set this up? So, okay, what I'm trying to understand here is if I use torch.save and pass in model O1 and then save it as my underscore model O1.pth, if I run this, then the model is going to be saved over here. Yeah, this is our model. And then I should be able to load it back as well. Okay, let's continue reading this. So the point of saving the entire model is that it includes the structure as long as the class is available when loading. So you can just load it directly having to define the without having to define the model architecture again. But if you move the saved model to a different environment where the class isn't defined, then it's a problem. In contrast, state dict is safer for sharing models because you just need the architecture code separately. Okay. Therefore, the user's initial thought might be incorrect. Saving the model itself does save the structure, but it's dependent on the code. The reason to use state_dict is for better portability and control, while saving the entire model is convenient when you have when you have the same code base. Yeah, no, I'm still not getting it. There is definitely something that I'm missing here. Now, if I keep asking questions to DeepSeek, then I'm gonna be reading the thought process each time. So here's what I'm gonna do. Okay, I'm gonna try asking Sonar instead, and then I can have like follow-up questions. Oh God, I forgot to change the model. Okay. Uh, when using torch.save in PyTorch, you have two primary options for saving models, saving only the model's state dictionary or saving the entire model. Each serves distinct purposes depending on shit. I missed the ad timer. So there's probably going to be an ad playing and oh, there's the ad. So I'll see you guys in 30 seconds. I'll take a little hydration break in the meantime. All right, welcome back. So, where was I? Each serves distinct purposes depending on your requirements and comes with unique pros and cons. Saving the model state dictionary. What is stored? Only the model's learned parameters, which is weights and biases, and buffers. Okay, how to save? Okay, how to load? Okay, advantages, flexibility. You are not tied to the specific saved class or directory structure. You are not tied to the specific saved class or directory structure. The saved state dictionary can be loaded into any compatible model definition, allowing fine tuning or reuse of weights or for other architectures. Okay, so I think what I'm getting here is that saving the model, like if it's saying that this specific, like you can save, it says you're not tied to the saved class, right? To the specific saved class. So I think you might be able to change things around, um, if you need to. Maybe not necessarily change the entire structure of the network, but you would be able to change a few things here and there. And that's why you're able to load these weights into, you know, any other program where the class is defined. But loading the model itself along with the quote unquote structure, it somehow it's tying it to something. I just need to figure out what that thing is. It's tying it to something either in the current project or in like the definition of the network, in the definition of the class. I haven't figured out exactly what it's being tied to, but that is kind of what makes it, let's say, not so convenient. Okay, portability. It avoids dependencies on exact Python code versions and is therefore less error prone when used across different environments or refactored projects. Okay. Lightweight. The saved file on the saved file contains only learned parameters, reducing file size compared to saving the entire model. Disadvantages: it requires redefinition. What? No, it requires redefining the model's architecture in code before loading the weights. That makes sense. Okay. Saving the entire model. What is stored? The complete model, including its including its structure, parameters, and data via pickle serialization. How to save, how to load. Okay. Advantage, convenience. This saves both the model architecture and parameters in one step, making it simple to restore with minimal code. It's faster to set up as you don't need to redefine the architecture when reloading. Disadvantage, tight coupling. The saved file is tightly bound to the specific class definition and directory structure at the time of saving. Any changes to the structure or Python environment may render the saved model unusable. Examples include class relocation, renaming, or refactored imports. And it's less portable. It's harder to share or reuse across different projects. Understanding the purpose of saving the entire model. When you directly save the model, the resulting file doesn't explicitly store the network architecture code itself, but a reference to the class definition. This means that the architecture must exist. Oh, now it makes sense. It's storing a reference. It's storing a reference to something. It's not storing the, so technically it's not storing the structure at all. This means the architecture must still exist in Python code during loading. While this method stores more than just the weights, example custom objects within the model, it's mainly useful for quick experimentation where you don't need to share or migrate the model to a different environment, and scenarios where refactoring or environment portability is not a concern, such as saving checkpoints for local inference or training resumption. The main downside is that refactoring or using the model on a different system can cause issues if the original code structure isn't preserved. Okay, so I'm kind of understanding what the issue is here, and it has to do with the fact that it's not storing the actual code. It's not storing the actual structure. It's storing a sort of reference to the structure, and if you change things in the original thing that the reference is pointing to, then that reference kind of breaks. That's, at least that's what I'm getting so far. But I feel like I need to understand how pickle serialization works in order to properly understand why this doesn't work well. Why saving the model isn't the most portable thing, because this is not convenient, right? It's kind of risky then, because you can't move this serialized object to a different project. You can only move the weights, but you would still need the class definition, right? You would need the structure to be defined explicitly in every single project that these weights are going to be used in. So essentially, you need to redefine the network in every single project where you're planning on using these weights. You can't just move the entire structure. You know what? Let me try and dig a little more. I'm kind of understanding what's going on here, but I feel like I don't fully understand. It seems like when you save a model, when you save an entire model, not just the weights, using torch.save, it doesn't save the structure, or rather, it doesn't save the entire class definition, but rather a reference, rather some sort of reference to the definition. Due to this, the file or the model cannot be reliably loaded in a different environment because the the saved file only contains a reference, not the actual structure of the network. I guess I need to understand how the saving process works in order to understand what exactly is being saved and how it's being saved. Let's see. Yeah, I think I need to dig into the pickle module because I dug into it a little bit a while back, but then I kind of just stepped away from it because I had to do some other stuff. Um, Give me a second. Let me scroll back up. Okay. So when you save an entire model using PyTorch, what when you save an entire model in PyTorch using torch.save, the saving process utilizes Python's pickle module to serialize the model object. Here's what happens during the process and why it behaves the way it does. How saving a model works. Serialization with pickle. Python objects, including Python models, are serialized using the pickle mechanism during torch.save. For a model, this includes the state, which is the weights, along with a reference to the model's class definition and its path within the code base. There it is. Okay. Okay. So that's what's being stored. And because that's what's being stored, um, if it doesn't exist, then there's nothing to reference. And obviously, if you're bringing this into a new project which doesn't have the class definition, this is definitely not going to exist. So it's like the reference is broken then. Okay, what is saved? Weights, weights and parameters, the learned weights and buffers of the model. I need to look into what exactly buffers entails here. But that's later. Then reference to the model class. The pickled object includes metadata pointing to the Python file and the class used to define the model, but it does not save the actual class code or architecture implementation. There's our issue. So it's not really saving the entire model. It's kinda, well, it's saving, but like in a not so portable way, because what it's saving is a reference. And then other internal Python objects tied to the model. Example, certain settings. What is not saved? The actual source code of the model's class, i.e. the architecture or logic of your model is not stored. Only a reference is included, which assumes that the same class definition exists at the time of loading. This is okay. So now it makes sense why it kept mentioning directory structure here. Where was that? Was that here or up here? I think it was up. I think it was up here. Yeah, it kept mentioning this directory structure. Now it makes sense why I was mentioning that because it's it's storing a reference to wherever the class is defined, and that class is defined in some file, right? So it's kind of it has to know where to find it, and that's where directory structure comes in. Give me a second. Okay. Um, Yeah. What's not saved is the actual source code of the model's class, i.e. the architecture or logic of your model is not stored. Only a reference is included, which assumes that the same class definition exists at the time of loading. why the saved model cannot be loaded reliably in a different environment. When you attempt to load the model in a different environment, Python's pickle looks for the exact class definition specified in the saved reference, including its name and file path. If this class definition is not available in the environment or has been moved slash renamed, the loading process will fail because pickle cannot resolve the references. This tight coupling to the original code structure makes the saved model non-portable across different systems or projects. Purpose and use cases for saving the entire model. Despite its limitations, saving the entire model has some valid. Okay, so what I'm wait, we'll continue reading this, but real quick, what I'm getting here is that just saving the Python model, um, well, I'm not going to be able to save the Python model. That's what I'm getting. I'm not going to be able to save the entire Python model. I can save all the weights. Give me a second. Okay, yeah. What was I saying? Hold on. I lost my train of thought. I got distracted by something and I lost my train of thought. Um, what I'm getting, I was talking about something that I'm getting. What I'm getting from this is that, um, shit. I was saying something and I forgot. Okay, anyways, so, um, I guess what I was about to say is that what I'm getting is that if you are trying to send the entire model to somebody, you can reliably only send the weights, and then the model has to be defined on their end. Um, but if you are looking to send the entire model, maybe exporting it to a different format might be helpful. And I guess it also makes sense um, why in Hugging Face transformers you have the models defined. So I don't think they're loading the entire model. What they're loading is the weights. Because if it's a PyTorch model that's being usually it's a PyTorch model unless you explicitly try to use something else like I don't know, Keras or TensorFlow or whatever. Unless you're explicitly trying to use one of those, it's most probably going to be using PyTorch by default. Um, Usually, I don't think it contains the structure of the network. I think they already define the structure of the network within their library. Anytime they try to add support for a different ML model or deep learning model, they define the network on their end. They define the structure on their end, and then all you are doing is loading the weights. Um, well, you're to be honest, you're not even loading the weights. The library is loading the weights because all you have to do is say I want so and so model, and then it knows where to download the weights from. Though you could, because they have defined the entire structure for you, you could technically load your own weights in there as long as you provide it with like properly structured weights that can be matched to the neural network architecture. You technically you would be able to just plug in your own weights. I'm not seeing why you couldn't do that. Also, yes, I was mentioning this at the beginning of the stream that I do want. Wait, did I mention? I don't know if I mentioned this. At some point later, once we get back into Hugging Face Transformers stuff, I wanna look into exploring the structure of every single model that we are using. So let's say, for example, we are using a language model that takes an input and gives an output. we have to load the model at first, right? So I need to find a way. I'm pretty sure there's a way. It's not going to be like, hidden away. It's just that I haven't found it yet. Um, but I want to be able to do this, basically this, so I can see the structure. And something similar was being done here as well. This was the VGG16. This is a convolutional neural network. Yeah, yeah. I wanna be able to explore the the structure of the models that we are using, because I definitely want to explore. I definitely want to study all of the models that we are using. Maybe not all of them because it's going to be time consuming, but I do want to get an idea of, or I want to kind of be able to visualize the models that we are using, if that makes sense. I want to be able to visualize what the model looks like or what components the model contains. So it's going to be a little less black box for me. And I mean, to be fair, in the beginning, I may not necessarily know much about what I'm looking at. Like, for example, with convolutional neural networks, I know visually what they could look like, but like how each of the components interacts with each other, how each layer interacts with the other one, and how different types of functions are included and what they do. All of that stuff, I don't fully understand it just yet because I haven't taken the time to, dive deeper into CNNs. But we are getting there. We are definitely getting there. Now that I've cleared my doubt about saving models and also loading models for that matter. So now I understand why saving the entire model is not going to work out. Wait, hold on, did I finish reading this thing? No, I'd stopped myself. I'd interrupted myself. So let's finish reading this, and then like I kind of understand now, thanks to, this research. I understand why we would need to why saving the entire model doesn't work, and you would need to have the network structure defined in whatever project you are trying to use the weights in. So what you are able to reliably save is the weights. And most of the time that's really what matters, because the weights carry a lot more, they carry a lot more, well, weight, because the weights are what actually, the trained weights, not just any random weights. The trained weights are what actually make the network work, right? You can, whatever the network is, you can like define the structure yourself, but the trained weights, you can't just get those weights. You can't just define them. You would definitely need to save the weights after a very tedious training process. So the weights are a lot more valuable, and that's what we are able to save using torch.save. Okay, let's finish. Oh, also, yeah, I was also mentioning that in terms of saving the structure of the network, one method is exporting it to a different format like Onyx, which I'm planning on doing. And that would be interesting to it would be interesting to see how that works, first of all, but also how well or how not so well it works. Like what are the pros and cons there? Because in that case, I'm assuming we are we are definitely exporting the entire architecture, because the entire architecture is being translated to the Onyx format. It's being recreated in the Onyx format, and then you also have the weights being passed in. The weights are also being saved along with it. Um, but yeah, that would be interesting to look into. I mean, I'm gonna look into it eventually. Oh, I also need to. Yeah, I'd mentioned this earlier. I also need to look into what else you can save to, like what other format you are able to save to using Torch Dynamo. Because I know that we can save to Onyx, right? So that's why we have this section, Torch Dynamo based Onyx exporter. But what else can it be? What else can Dynamo export to? Okay, yeah, I'm gonna look into this at a later time. Right now, we have a couple of other things to explore. Okay, where was I? Yeah, purpose and use cases for saving the entire model. Despite its limitations, saving the entire model has some valid use cases. Quick prototyping. In small scale projects or experiments where you do not change or refactor the code, this method is convenient because the entire model can be restored with minimal effort. Example, saving intermediate checkpoints during training for later use in the same code base. Ease of use. This approach requires less boilerplate compared to saving and reloading state dict, since you don't need to reinitialize the model class manually. Handling custom components. If your model includes custom logic or objects beyond the state dict, these will also be serialized. For example, models containing non-standard components like layers or configurations that are part of the model's class can be saved directly. Comparison with, give me a second. I just realized why that was so loud. Because yesterday I had rated a person. They were super nice. It was a nice, comfy stream. Um, but their volume was pretty low, and that's why I had to turn my system's volume like really high to be able to hear them. And I forgot to turn it off. And I was wondering why a bunch of the other streams that I loaded, they were coming in a little louder than usual. Like usually they wouldn't be that loud, but then today they were loud. And I just remembered that, oh, okay, this is what I was doing yesterday. This is what I had done yesterday. Give me a second. Okay. All right. Cool. Um, right. So here is a comparison, and then there's a little more, and then we can move on. Okay. Comparison with saving state dict. What is saved? Weights, buffers, and a reference to the class. And in state dict, it's just weights and buffers. Then code dependency. Class definition must match the saved reference. This requires manual recreation of the architecture. Okay. Portability across projects. Low, high. Okay. File size larger, smaller. Okay. Use case. Same environment setups and checkpoints. Flexible reuse across environments and projects. Best practices for most scenarios. It's also suddenly it's becoming clear to me why saving an entire model is kind of a legacy feature. Like they mention it here somewhere. um because this involves loading the model, which is a legacy use case for torch.save. Yeah, suddenly I'm seeing why it's a legacy use case. I don't think it's meant to be used all that much, at least in production. It's not going to be used nearly as much as weights only. Okay, for most scenarios, it is recommended to save the state dictionary as it's more portable and provides greater control over the model architecture. Something I want to experiment with is what happens if I try to load um, what happens if I make a slight change to the architecture and then try to load the weights into this changed architecture? Like how are the weights going to be fit onto the new architecture? That would be something interesting to explore. Okay, if you decide to save the entire model, ensure that the code environment remains unchanged for future loading, or you may encounter compatibility issues. In conclusion, while saving the entire model provides simplicity for certain use cases, its reliance on Python's pickle for class references and structure makes it less reliable across different environments. Understanding these nuances allows you to choose the saving method that aligns best with your project requirements. Yes, yes, it does. Okay, so now I get it. Now I get it. And okay, so I still need to explore the training side. Well, I mean, I've already explored the training side of neural networks, like how to train neural networks, but I kind of need to get back to it and kind of study it properly, because previously it was just kind of, just 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 touching it, if that makes sense. It was just like, how do I say this? I just barely scratched the surface of what it is to train a neural network. Now I need to go and explore it properly and understand the various functions, stuff like loss functions, for example, because there's multiple different loss functions. I need to explore what each of those are and how each of them differs from one another. There's a bunch of exploration. Now that I think about it, there's a bunch of exploration that I'm yet to do, even in terms of feed forward neural networks, because we have the layers, right? We have the linear layers. That's your basic feed forward neural network. But in between the hidden layers, you have nonlinear activation functions, and you don't just have ReLU. You have a couple of different nonlinear activation functions, right? I don't remember if softmax also counts as a nonlinear activation function, but you have softmax as well. So there's a bunch of these that I have to explore. I don't I don't know how many of them apply strictly to feed forward neural networks, though I don't think it has to be strictly applied. Um, that's kind of where wait, give me a second. Hold up. Deploying models in production. I'm interested in this section. And this brings us to Onyx. Okay. Right. So I'm on the right path, I guess I could say, because I've seen Onyx support in a bunch of different languages and a bunch of different platforms. Like Unity as well has Onyx support through their Centis package. And that's also another reason why I was so interested in Onyx. It's because learning how to export to Onyx is gonna allow me to bring neural networks into Unity, of course, through Centis. And there's a bunch of exploration that I have to do around Centis as well. But I kind of wanted to get my basics down first, through PyTorch, get my basics down with PyTorch before going towards that side. Now, let's just type ReLU. Okay, this is what I was looking for, torch.nn. And I think under torch.nn we have yeah, nn.relu, nn.linear. Yeah, okay. I just remembered it. Right. So here we have nonlinear activations and nonlinear activations others. I'm not sure what that is, but yeah, these are a bunch of the nonlinear activation functions. There's a long list of them. There is a long list of them. But like I mentioned before, I'm not sure how many of them apply specifically to feed forward neural networks. I'm pretty sure a bunch of these are for a couple of different types of networks, not just feed forward neural networks. There's some that are probably meant for more advanced architectures or architectures that I haven't yet explored myself. Oh, and then there's these as well. Wait, so okay, softmax comes under the other section. Softmax, at least in classification neural networks, it mainly gets applied at the end. At least in like the simpler ones that I've seen, it mainly gets applied at the end, so we can get the probabilities. Though, okay, something worth exploring is what if we don't apply softmax? Because it kind of seems like softmax takes all of the values that you get from the neural network and it scales them down. The result of a softmax function is that whatever set of values you have given it, it's going to scale them down such that the sum of all of them is one. And that's kind of how you get your probabilities, at least in classification situations, but I'm pretty sure in others as well. That's kind of how you get your probabilities. So I need to. I want to see. I want to see what happens if you don't apply a softmax function at the end. Like, is that going to make a difference in the result or how the result gets perceived, or does applying a softmax function give us a more standard way of dealing with the result? Because if we know that the softmax function is going to be, you know, a set value, that the softmax function is it's going to give us the result. Sorry, the result of a softmax function is going to be a set value. It's just going to be all of the values are going to be scaled down such that the sum of all of them, the sum of the entire set, is equal to one. So that gives us a sort of standard that we can work with and work around. I'm not sure what terms to use here, but you can make assumptions there. You can make assumptions when you know that, hey, this is what's going to be the result. Okay. All right. Now, give me a second. All right. Okay. So here's what we're gonna do. Okay. I'm gonna raid somebody. They are learning about mushrooms right now. Their name is Ceres VT, I think. They're learning about mushrooms. Um, yeah. So I'm gonna go raid this person. Marty and Cutane, thank you very much for stopping by and thanks for hanging out. Anyone else who might have been lurking in the chat, thanks for hanging out. I did want to go a little longer today, but I have some stuff to do because of which I have to end a little bit early. And I'm also gonna hang out in this person's chat for a little bit and then go do the other thing that I had to do. But yeah, okay, that's going to be it for today's stream. Hopefully, I'm able to do another talking stream tomorrow as well. But if not, then I'm going to try and do a mute stream, definitely. I want to get this TTS thing up and running as soon as possible so that even the mute streams are not going to be mute streams, they're going to be AI voice streams. But yeah, anyways, that's going to be it for today's stream. I hope you guys have a nice day, and I'll see you all next time. Peace.